Alright, thanks for watching, and today I want to show you a really cool fact. Namely, any metric space S, no matter how incomplete, can always be completed. That is, there's always going to be a larger metric space that contains S such that that larger metric space is complete. In other words, the fact that we can complete the rational numbers to get the real numbers isn't very surprising. This holds really for any metric space. But we just have to be a bit more careful, and you'll see why. So, again, let SD be a metric space. Alright, and how are we going to do that? Well, just consider the set of all Cauchy sequences in S. So step 1. Let C be the set of all Cauchy sequences. In S. And define the following equivalence relation. Just say that Pn is equivalent to Qn, where if the limit as n goes to infinity of the distance between Pn and Qn goes to 0. And one can show, similarly to the video of the completion of the rational numbers, that this is an equivalence relation. So then squiggle is an equivalence relation. And therefore, we can just let S prime be the set of all equivalence classes of C. So step 2. Let S prime be the set of all equivalence classes. Of C. In other words, consider all the Cauchy sequences except that we just say two Cauchy sequences are equal if the following property holds. And before I continue, we will prove a very useful lemma that we'll use over and over again. So, and you'll see in a second what we'll do. Because look, we got S prime, but we still need to find a metric on this. So just a quick lemma. In general, if you consider the difference, I think dxy minus dpq. So a lot of times what we would like to interlace the two things. So, and it turns out it's always true that it's less than or equal to dxp plus dqy. Alright, and how do you show this? Well, just consider the following. So dxy, just split it up in dxp plus dpq plus dqy. And let's just put this dpq term here. So then what we get is dxy minus dpq. It's less than or equal to dxp plus dqy. And similarly, you can do the same spiel with dpq. So in general, dpq, that's less than or equal to px plus dxy plus dyq. And again, put the dxy term here. So we get dpq minus dxy. It's less than or equal to, if you want, dxp plus dqy. Okay. And then essentially you're done, because here you're saying that x here you're kind of saying x is less than or equal to a constant. Here you're saying minus x is less than or equal to a constant. So the absolute value of x is less than or equal to that constant. So the lemma has been shown. And now let's continue with our step 2. So now what we want to do, we want to define the following metric. So again, S prime was just the equivalence classes of Cauchy sequences. So it's equivalence classes of Cauchy sequences where Pn is Cauchy in S. And now define the following thing. Define the distance between Pn and Qn to just be the limit as n goes to infinity of the distance of Pn Qn. And there are a couple of things we have to show. So first of all, we have to show that this limit exists, and we have to show that it's independent of the choices of sequences that we put. So first, let's show that this limit exists, and for this, essentially it's enough to show that this sequence, I believe is Cauchy. I think that's all, right? Yes. All right. Then, what do we get? So d Pm Qm minus d Pn Qn. So what we want to show this is eventually small. But now, notice we can use our interlacing lemma. So this is less than or equal to d Pn and then plus d Qn. But the point is, if m and n are large enough, because Pm is Cauchy, by definition, we can make this less than epsilon over 2 for any epsilon, and we can make this less than epsilon over 2 for any epsilon. So this is less than epsilon, so if m and n are large enough, so bigger than capital N, for some capital N. And so in particular, what does that show? It shows that the sequence Pn is Cauchy. So, this thing, the distance, sequence of distances, is Cauchy. But careful, it's not just a Cauchy in S. This is a sequence of real numbers. So it's Cauchy in R. So because R is complete, and again we have already shown this, so since R is complete, the limit of that exists, and that's what we call dPn Qn, which is the limit as n goes to infinity of dPn and Qn exists. So the limit exists, and moreover by existing we mean finite. Alright, so that's good, and then let's also show that it's independent of the choice of the sequence. So suppose, let's say Pn is equivalent to P prime n and Qn is equivalent to Q prime n. What we want to show is that the distance of Pn Qn is the same thing as the distance of Pn prime Qn prime. So show. In other words, what we want to show is that the limit as n goes to infinity of d Pn Qn, it's the same thing as the limit as n goes to infinity of d Pn prime Qn prime. Because you see this becomes capital D of Pn Qn, and this becomes capital D of Pn prime Qn prime. But again, the proof is almost the same as the one I just erased. Namely, you just use that interlacing lemma again. But then let's consider just the difference between Pn and Qn and Pn prime and Qn prime. Again, by that interlacing lemma, this is less or equal to the d of Pn prime, and d of Qn prime. But as n goes to infinity, this goes to 0 because of the definition of squiggle. Remember, squiggle means eventually this distance goes to 0. And similarly, this distance goes to 0 as n goes to infinity. So if you want by definition of squiggle, so eventually if you let n go to infinity, this actually goes to 0. And therefore, what do we get? The difference in the absolute values goes to 0, so this limit goes to that limit. And therefore, it's a well-defined thing, and you can also show that it's symmetric. So D is well-defined, and also D is a metric. And it's quite immediate to verify. For instance, let me verify the triangle inequality. So dPn Rn, that is again the limit as n goes to infinity of dPn Rn. Okay, it doesn't matter which sequence we pick now, but it's less or equal to the limit as n goes to infinity of dPn Qn plus dQn Rn. But that's equal to the limit as n goes to infinity of dPn Qn plus the limit as n goes to infinity of dQn Rn, and that is d of the class Pn Qn. So the difference between the equivalence classes plus the difference between those two equivalence classes. That's what we want to show. All right, so what do we have? We have this space S prime with the metric D, and now we want to show that this space S prime actually solves our problem. So what's next to show? Well, what do you want to say? Yes. So we have shown that S prime is a metric space, but another thing we want to show that it actually includes S. Now, of course, S prime doesn't include S per se, because elements in S, they're just numbers, or like think rational numbers, but elements in S prime, they're Cauchy sequences, and those are not the same thing. But what I want to show is that there's actually, you can sort of think S being a subset of S prime in the following way. Namely, there's a very easy way of associating an element in S, an element P in S, with a class P bar in S prime. Namely, consider, so if P is in S, consider just a constant sequence. If you want P bar to just be the sequence P, 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 it's almost like a robot. Then, okay, here's the thing, well, this is a Cauchy sequence, so in particular, P bar is in C, and therefore the class of P bar, well, by definition, that is in S prime. So we get this, and moreover, well, this association, let's call it phi, between P and P bar is 1 to 1. Moreover, if you want phi of P equals P bar is 1 to 1. And that's because, you see, if P is not equal Q, then of course P bar, which is P, 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 is not equal to Q bar, which is Q, 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 Q. But not only that, if you take the difference between the nth term of the sequence here and the nth term of the sequence here, then it can never go to 0. Moreover, and the distance of p bar, if you want, distance of the nth term, p bar n, and a q bar n, well, that is the distance of p and q. Well, and that's never goes to 0. So in fact, p bar is not equivalent to q bar, so they can't be in the same equivalence class. So that's why the class of p bar is not the same as the class of q bar. So phi of, and therefore, if we want the association that takes p to the class of p bar and the association of q that takes q to the class of q bar, so if you want p bar is not equal to q bar if p is not equal q. And so this association is 1-to-1. And moreover, the nice thing is, and you may have realized this here, this association, well, it preserves the metric. So moreover, what is the distance of p bar and q bar? Well, by definition, that's the limit as n goes to infinity of the distance of the nth term of here, which is p, and the nth term here, which is q, and that just gives you dpq. Okay. So not only that, so we have basically a very natural association between elements of S and classes in S prime in a way that the distance is almost kind of preserved. So it's called a isometric embedding, if you want to know the technical term. All right, and last but not least, we need to show that this space is complete. So that is the big last step. So step 4. So claim. So we want to claim that S prime and D is complete. So let PK, okay, let's do it with a capital, let me see, PK, PK Ponky Kong, be a Cauchy sequence in S prime. And what we want to show is that PK actually converges to some element in S prime, but remember with the metric of D. Now, here's the thing, remember PK, that's an element of S prime, so it's an equivalence class of sequences. So it's of the form PKN, where n is a natural number. So it's very important to understand there's a difference between K, which is the kth element in S prime, and n, which is just the element of the sequence. Now, here's the thing. So PKN, so for every fixed k, this sequence is a Cauchy sequence, just by definition of C, sorry. So for each k, what do we know? We know PKN is a Cauchy sequence. So in particular, one thing that we can show is that there is capital N such that if M and N are bigger than capital N, then the distance between PKN and PKN is less than, well, epsilon, but here let's pick epsilon to be 1 over k. You'll see why we need that. It's so cute. It almost looks like pumpkin pumpkin. Right? Okay, but joking aside, the thing is this holds for capital N, but basically after that threshold, this is always true. So after that threshold, the terms of your sequence are very close together. So at most 1 over k together. So without loss of generality almost, we can just assume that capital N is just the initial term. And if you want to be picky, the reason is we can just consider otherwise the following sequence. So by considering the following sequence, P star Kn, which is just P, K, but it starts at capital N if necessary. And you can show it's Kokoshi with this sequence. Assume for all M and N, we have the distance between PKM and PKN is less than 1 over k. So already initially, all the terms of the sequence are close together. And here's why we need that. So what do we get? And that's quite interesting. In particular, for k equals 1, we have P1, which tells you P11, P12, P13, P14, etc., where all the terms are at most 1 apart. For P2, I don't even know if I wrote this like this, so for P2, we have the terms P21, P22, P23, P24, which are at most 1/2 apart. For P3, we have P31, P32, P33, which are at most 1/3 apart. And maybe you might see where this is going. Remember, we need to find a limit of the PKs. Well, just consider the diagonal sequence. So consider Qn to just be the sequence PNN. Like CNN, but with P, where N is an N. Well, ideally, I want to claim that PK converges to the equivalence class of Qn, but first of all, what we need to show is that Qn is Cauchy, just so that the equivalence class is in fact in S prime. Right. And now let's show the following. So I'm claiming that Qn, as just defined, is Cauchy. And we really need this because then once it's Cauchy, the equivalence class is in S prime. So then we have a good candidate for the limit. And here's a proof. So let epsilon be given. Now remember, we know that PK is Cauchy just by assumption. Then since PK is Cauchy, there is capital N, large enough so without loss of generality, assume it's greater than 3 over epsilon. So we'll do an epsilon over 3 argument, such that if K and L are bigger than capital N, then the distance of PK and PL, which I would like to remind you is just the limit as n goes to infinity of the distance of PKN and PLN is less than epsilon over 3. Where? What is PKN? Well, just PK, just a representative of the equivalence class. And similarly for PLN. All right. Then, the point is, with that same n, what do we have? If K and L are bigger than a threshold, then we have something beautiful and miraculous? Well, let's consider, right, the difference between QK and QL. Because ideally we want to show this is small to show Qn is Cauchy, but by definition of Q, that is PKK and then PLL. And now let's kind of use this identity. So this is less or equal to the distance of PKK and then PKN plus the distance of PKN and then PLN plus the distance of PLN and then PLL. And I know, it's just ridiculous, but here's the thing. Remember that for fixed K, again, the way we defined, I believe, our sequences, for fixed K, this thing is less than 1 over K. So that's how we defined Qn, okay? And we defined our PK. And moreover, same thing for here. So we know that this is less than 1 over K, and similarly, we know that this is less than 1 over L. And not only that, the point is this limit is less than epsilon over 3, so we can actually also make that, so again, for fixed n, we can also make that less than epsilon over 3. So in the end, what do we get? If you want just slightly slower, so that's less than 1 over k plus d pkn and then pln plus 1 over L. The point is we can make this less than epsilon over 3 because the limit of this is less than epsilon over 3. And last but not least, what do we know? We know that K and L are bigger than capital N, which is bigger than 3 over epsilon. And so 1 over K is less than epsilon over 3. So this becomes less than epsilon over 3, epsilon over 3, epsilon over 3. So it's like Beetlejuice, 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 and we get epsilon. So in fact, that's very good. We have that Qn is Cauchy, and then last but not least, we can prove the convergence theorem in a very similar manner. Last but not least, in the final step, I don't know which step, let's say step 5, let's show that pk actually converges, as k goes to infinity, to the equivalence class of Qn. Because then we would be done. Because Qn, we've shown it's a Cauchy sequence, so by definition of the equivalence class, we know this is an S prime. So pk would converge to something in S prime, so the proof would be complete. No pun intended. But now, let epsilon be given. Then use the fact that Qn is Cauchy. So since Qn is Cauchy, there is capital N, and without loss of generality, assume it's bigger than 2 over epsilon, such that if k and n are bigger than capital N, then the distance between Qn and Qk, it's less than epsilon over 2, which really means the distance between Pnn and Pkk is less than epsilon over 2. All right, but now let's consider the distance between pk and this equivalence class. Then the distance between pk and the equivalence class of Qn. remember by definition, so if you want, that's a distance of the equivalence class of pkn, pecan, man, after pumpkin there's pecan, and pnn, or qn, sorry. And by definition, that's just the limit as n goes to infinity of the distance of pkn and qn, which is pnn. Okay? So that's just what qn is by definition. And we want to show that this limit is 0. But look. So in other words, we want to show that there's a n large enough such that this thing is less than epsilon. But then, but let's say the d of p, kn, and pnn, well, you can just split it up as follows. So this is less than or equal to d of pkn, and then pkk, plus d of pkk and pnn. Now here's the thing, remember for fixed k, this becomes less than 1 over k. And this becomes by definition less than epsilon over 2. So the point is, if you pick n large enough, or sorry, that's yeah, all right. So the point is, so this is true for every n, at least large enough for every n bigger than capital N. And the point is, therefore, if you take the limit of this as n goes to infinity, so the distance of pk qn, which again is the limit of this gibberish, n goes to infinity of d pkn pnn, that becomes less than or equal, less than or equal to this thing, 1 over k plus epsilon over 2. And last but not least, just pick k large enough such that this is less than, no, I think by definition k, it's bigger than capital N, which is bigger than 2 over epsilon. And so by definition, this is less than epsilon over 2 plus epsilon over 2, which becomes epsilon. So if k is large enough, then we get that the distance between pk and qn is less than epsilon, and therefore the limit as k goes to infinity of this distance, the limit as k goes to infinity of pk, it's qn. And therefore we're done, so the proof is complete. So if you like this and want to see more math, please make sure to subscribe to my channel. Thank you very much.